Next, let's talk about a different kind of tree structure. It's called a trie. Another name for it, and probably the better name for it, is prefix tree. The goal of a prefix tree is to be able to insert words in constant time. By word, I mean a string of characters. That's usually what tries are used for, strings of characters, usually not integers and other types of values. So we want to be able to insert a word in constant time. When we say constant time, that also could be, the size of the word itself, because to insert a word, of course, we have to go through every single character of that word. So maybe a better way to say this would be O of n, where n is the size of the word. But we also want to be able to search for the existence of a word in constant time as well. Given some word, we should be able to check does it exist or not very efficiently. Now you might be thinking, can't both of these operations most easily be achieved using like a hash set? And the answer is yes, but there's one last operation that a hash set can't get for us. Maybe the most important operation is being able to search for a prefix. That's why we call this a prefix tree. What I mean is we could insert and search for a full word. For example, apple. We could also do that with a hash map, but with a hash map, we can't search for prefixes. What I mean is, given a prefix like just AP, we want to know, are there any words in our prefix tree with this prefix? Obviously, the word apple does match that prefix. So with a prefix tree, we would be able to return true, and we would be able to do it efficiently, O of 1, aka the size of the prefix itself. But with a hash map, there's no easy way to do this. We would, in the worst case, have to go through every single string that we inserted into the hash map. So this is the problem that we're trying to solve. And before I get into the implementation of this data structure, an application for this would be with search engines or any kind of searching at all. For example, when you use Google search and you start typing a few characters and it auto-completes or it gives you a few suggestions, it essentially uses a prefix tree. It uses the prefix that you type in and it checks what strings match that prefix. So it definitely is an important data structure, and it's definitely one that can also come up in coding interviews. The good thing is that it's actually easier to implement than you might expect. So let's get started. Like I said, a trie is essentially a tree of characters. So each node in this case is going to be a character. And the most common restriction, especially for coding interviews, is that we only have to worry about lowercase letters from A through Z. But even if we had a larger character set, it wouldn't make a huge difference in the structure of this. We could have A through Z and capital A through Z. We could have, larger alphabets. It doesn't really make a difference. Lowercase a through Z gives us 26 characters we have to worry about. So in that case, we would have a tree that looks something like this. You can think of it as having a single root node that's empty. The root node won't really have anything. Or maybe a better way to think about it would be we have 26 root nodes in this case, one for each character that we're worrying about. What that essentially means is that all the words that start with the character A are going to go down this path in the tree. Obviously, I haven't drawn all 26, that would be too large, but this character, lowercase character A, is going to have all words that start with the character A. So, this is going to have children from A to B to C to Z and all those 26 characters. And each of those are also going to have 26 children at most. I mean, it doesn't necessarily have to actually have any children at all. But if we were, for example, looking for the word apple, we would of course want to go to this branch because apple starts with the character A. What's the second character of apple? Well, it's P. So then we would go down this path. And at that point, we would check, do we have a second P in here? If we do, then, we keep going down that path. We're still looking for the word apple, but maybe we don't have a P here. We haven't inserted that character. Maybe we have an E, but that's it. We don't have any other children here. Then we know for sure we can't possibly contain the word apple because this is where it would be if we had inserted it, but it's clearly not here. So we have not inserted the word apple. Now, another thing to note about this tree is that since each node could have up to 26 children in this case, but it could also have 0 children or any number in between 0 and 26. So it doesn't really make sense to give every single node a left and right pointer or define a variable for every single child anyway. An easier way to do this would be a hash map. So every node is going to have a value, but also it's going to have a hash map of all of its children. And the key of that hash map is going to be some character, from A through Z. So each character is going to map to some node. So this is what the code would actually look like. It might be a little bit unintuitive at first. Let's first focus on the trie node itself, and then we'll take a look at the full trie class. But a trie node has children, and in this case, this is a hash map in Python, so it's an empty hash map initially. And using a hash map makes it pretty flexible. We were talking about 26 characters, so we could have actually defined an array of size 26 if we wanted to, but a hash map makes it a lot more flexible. That's why it's easy to handle uppercase A through Z as well, or maybe any type of alphabet that we really needed to. For every node, we're also going to have a Boolean value to determine if this character is the end of a word or not. We'll get more into that later on, but for now, you can kind of ignore this. But notice how the trie node itself doesn't actually store any characters. We could store a character in each node if we wanted to, but it's redundant because you can see in our trie class, we have a root node, which is a trie node, and that trie node has 26 children. That's what I meant when I said we can kind of assume that we have an empty root node, which has up to 26 children. So for the root's children, if we access the children field and then we access maybe the A character, that is all the information we need. That's where the character is stored. It's stored as a key of the children map. It doesn't need to actually be stored in the trie node itself. That can be a little bit unintuitive at first. But I think after we walk through each of these algorithms, it'll start to make more sense to you. So let's say we created an instance of this trie, and the first thing we want to do is insert some words into it. Let's say the first word that we want to insert is apple. How would the search algorithm work? Well, of course, we're going to go to our root node, which is sort of the empty node. And we want to start going through every character in this input word apple, and we want to insert every single character into the trie. And it's really that straightforward. We're going to go through every character, iterate through it, and if that character has not already been inserted into the trie, meaning, A is not one of the children of the root node, then we're going to insert that A character. We're going to create a new trie node for the character A. Even though we're not passing A in as a parameter to the trie node, it's okay because the key of the hash map, of the children of the root node is the lowercase character A. So here we're going to say for the lowercase character A, we inserted a trie node. And then, initially our current pointer was here at the root. Now the current pointer is going to be shifted to the new node that we just inserted. So now our current pointer is going to be over here. And we're going to just go character by character at this point. It's just that straightforward. So P is not a child of A. So let's insert a new character for P, or a new trie node for P. So one of the children of A now is a new trie node. And for P, it also needs a child for P. And then this also needs a child for L, which needs a child for E. So we inserted our word apple. And the last thing we want to do before we return is for the last character, we have a pointer to this character, we want to mark it as the end of a word. So when we create every trie node, initially we set this variable to false. It's not the ending of a word, but after we insert the last character, we want to mark that as the end of a word. I'm going to do so with a green circle like that. I'll talk a bit more about that later on. Now suppose we want to search for a word, which is actually very similar to inserting a word. And let's say we're searching for the word apple, the word that we just inserted. So we would start at the root node. We would go character by character through the input. So we would start at the character A. We would check, is A a child of the root node? Yes, it is in this case. It's here. Now, if A did not exist, suppose none of these existed, we would see that lowercase a is not a child of the root. and then we would immediately return false. There's no need to go down this path because the character doesn't exist, then the word must not exist and we can return false. But in this case, it does. So what we would do is shift our pointer to that child here. And we do that with this line of code. And so we're going to keep doing that now for every character. Now we're looking for P. Is P a child of A? Yes, it is. And we can do that in constant time, by the way. For every character, we're simply iterating through every single character, and then the rest of the operations are constant time operations. That's why this search function can run in constant time or maybe linear time if n is, let's say, the size of the word. And you can see that that's pretty much the exact same for the insert function. It's also the same for the other function that we're going to talk about. So at this point, our pointer would be at this P. We would be looking for the next P. So is P a child of, this P? Yes, it is. And then we would move our pointer there. Now we're looking for the L. Is L a child of P? Yep, it's right there. So then our pointer would move here. Is E a child of L? Yes, it is. So now our pointer would be here. We iterated through every character for the word that we were searching for. Now, can we immediately return true? Well, not quite. We're going to return whether this character is the end of a word or not. In this case, it is. We marked that with a green circle. So we would return true in this case. The word apple does exist in our try. But what if instead we were looking for the word A? We want to know, does the word A exist in our try? Well, we would do the same thing. Start at the root. Does it have a child? That's the character A. Yep. So then our current pointer would be here. And that was the only character we were looking for. So our loop would have terminated. We'd be out here. And then we would want to know, is this the ending of a word or not? Well, it was never marked as the ending of a word. E was marked as the end of a word, but this was not. So we would return false. The word A does not exist in our prefix tree. And that makes sense because just because we inserted the word apple doesn't mean we inserted the word A or the word AP and every prefix of this word. That's why every time we insert a word, we mark the last character as the end of a word. Because then when we search, we don't want to say that, this is a word. We never inserted this word. We inserted apple. Suppose the next word that we want to insert is the word ape. So we call our insert function again. Our current pointer is going to be set to the root. We're going to go character by character in the word ape. Is A a child of the root node? It is, so we don't have to insert a new lowercase a. That's the point. We don't want redundant nodes. We don't need two lowercase a's that are both, children of the root. Because we want all words that start with A to go down this branch. We don't want to have to search two branches or multiple branches. We just want a single branch to be able to search for. So when we're inserting the word ape, we see the lowercase a has already been inserted. So we go to the next iteration. We're trying to insert the lowercase p. We see that's also already been inserted in the second position. So now we're trying to insert the lowercase e. That has not been inserted. So at this point, we can add a new character for the lowercase e. And the last thing we can do is mark this as the end of a word. So you can see as we insert each word, we're just going character by character. That's why this is so efficient. And this also helps keep our search efficient as well. So let's insert one last word, nope. We see that there's no root with the character N, so we can go ahead and insert that. And then for these, of course, we would just have to insert every other character, O, P, and E. So now let's move on to the last function, starts with, which is the main purpose of this data structure. Starts with doesn't necessarily take a word, it takes a prefix that we want to match to possible words that exist in our data structure. And we want to return true if there's any words that start with this prefix, and false if there's not. Suppose we're given a prefix no. So for this prefix, let's check, are there any words that start with the prefix no? At this point, you probably know exactly what to do because this function is similar to the others. That's why this data structure is actually a little bit easier than people expect. So we start at the root. Is there a child with the character N? This one. So then our pointer would move here. Are there any children for this node with the character O? Yep. This guy. And we can do this very efficiently because our children are a hash map. So we can check that very efficiently. So at this point, our loop stops because we went through the entire prefix. And since current is not null, our pointer is not null, we can return true. But if we ever got to a point where we were looking for some character and it didn't exist in our prefix tree, we would immediately return false. There's no point then to go through the rest of these characters. For example, if we didn't even have an N inserted into our prefix tree, then we could immediately stop. We wouldn't even have to go through the rest of the prefix. So a trie can be really helpful for searching for prefixes. It's also efficient for inserting and searching for words altogether. Oh, and I think I forgot to mention, we would have marked this E as the ending of a word as well, just to illustrate that. Instead of calling starts with on this prefix, what if we were just searching for this word? So we would call search, we would go character by character, we start at the root, N exists, so we move to it, O exists, so we move here. So this character exists, but is it the ending of a word? That's what we would return. Current.word, which represents a true or false Boolean value. In this case, it's not the ending of a word, so we would return false. While there are words that start with this prefix itself is not necessarily a word. So that's the distinction here. So if you just learned about prefix trees, I hope this was easier than you were expecting, and now you have a new data structure in your toolkit.